Alright, my dear children of class 11 science, we will continue with the concept of conduction of heat in a metal rod. Now in this particular video, we derive an expression of coefficient of thermal conductivity. Okay, so in order to derive this term that is called coefficient of thermal conductivity, we take a slab. We take a what? Slab. So as I said already, we take a slab, or we take a what? Slab, and this is a parallel face slab. This is a parallel faced slab. Okay. Now this has a cross section area, and even this has a what? Cross section area. And this cross section area of two faces of this slab are parallel to each other. Okay. And we take this surface. We take this surface also as a what? Isothermal surface. See, you will have learned already in the last YouTube video about isothermal surface. Now we take this surface as isothermal surface because we consider the heat flow from this surface and leave from this surface. So that means heat enter from this surface and heat leave from this surface. But the direction of flow of heat is perpendicular to the surface. So as for the consideration, I can take that if Q is the amount of heat that enters from this surface and Q is the amount of heat that leaves from this surface. And now these two surfaces, okay, are separated by a distance, say L. Okay, separated by a distance what? L. So as for the diagram, as I said already, students, so these are the two parallel face slab, okay, having a cross section area. Now I consider that cross section area is say A. If this slab has cross section area A, then this slab also has a cross section area what? A. Means equal cross section area. Okay. Now what is the distance between the two faces of the slab? Okay, that is L. Okay. Now the face, these two particular face, when the heat flows, maintain what temperature? Steady temperature. At the face, one steady temperature maintained at this face is say theta 1, and steady temperature maintained at this face is say theta 2. But these two temperature which maintain, that is theta 1 and theta 2, okay, which remain constant with respect to time, occurs only when the state which reach, that is called steady state. That means we derive the expression of coefficient of thermal conductivity under what state? Steady state. So that the temperature maintained at this phase is theta 1 and temperature maintained at this phase is what? Theta 2. And children, you know very well that the heat always flow from body at higher temperature to a body at low temperature. That means this is the phase where the heat is entering and this is the phase which heat is leaving. That means this arrow say that the heat is flowing from surface at temperature theta 1 and to surface at temperature theta 2, which means theta 1 is greater than what? Theta 2. So theta 1 is greater than what? Theta 2. That's why the heat flows from the surface at temperature theta 1 to surface at temperature theta 2. Now we make one important assumption out here, children, that is, we assume that there is no heat flows or there is no heat escapes out from the side of the slab. Side of the slab means this side of the slab, okay, through convection and radiation. Now in order to trap the heat, not to go out or escape the heat from the side of the slab, what we need to do? We need to cover this by what? Some insulating material. So in that case, what happened? The heat can simply flow from this face and leave from this face. Thus, the line of flow of heat, okay, at all points is always normal to this face. See, this is face, these are the faces where the line of force, this arrow indicate that the line of force, the line of flow of heat, is always normal, means what? Perpendicular to the surfaces. Okay. Now, under this particular circumstances and under the state which we are considering called what state? Under steady state. See children, this is very important. Under what state? Steady state. And this expression that we are going to derive is under what state? Steady state. So under this steady state, the quantity of heat that entering at this surface is Q, and the same amount of quantity of heat that leave from this face, that is what? Q. So let Q, I consider let Q be the what? Amount of heat entering, the amount of what? Heat entering, okay, on one face, okay, at a certain time interval, so that the same amount of heat will leave from the other surface at the same interval of time. That means I write down same time interval, so that I write down so that same amount of heat, amount of heat leaving from the what other phase, from the what phase, from the other phase in the same time interval, in the same time interval. So at a particular time interval, when amount of heat, like Q amount of heat, enters at this phase, at the same time interval, the Q amount of heat leave from this phase. Okay. So with this, we can easily see that what amount of heat that enters and leave at the same time interval can be observed experimentally. And when we see this particular part experimentally, it is observed that, so I write down experimentally, the amount of heat, that is Q, entering and leaving at a certain time interval, is directly proportional to the cross-section area of each phase. And you know what is the cross-section area of each phase? A. So A is nothing but area of what? Cross-section. Area cross-section of each phase. So there are two phases, parallel phases, having cross-section area A and A. So amount of heat that enters and leaves at a certain time interval, is directly proportional to the area cross-section of that phase, which means more the area cross-section, means more amount of heat that enters and leaves at a certain time interval. So this is number one. In the similar manner, the quantity of heat entering or leaving from the two phases is also directly proportional to the temperature difference, directly proportional to temperature difference between two surfaces. Now that temperature difference is nothing but θ1 minus θ2. So you know, first phase has temperature θ1, second phase has temperature θ2. The difference in temperature is θ1 minus θ2. Because I have already mentioned θ1 is greater than θ2. So temperature difference means θ1 minus θ2. But this quantity of heat is directly proportional to temperature difference. And this is nothing but what difference? Temperature difference. This is temperature difference between two phases. Between two phases. Experimentally, even it is observed that the quantity of heat that flows is also directly proportional to the time which is required to flow. That means the quantity of heat entering or leaving, from two phases is also directly proportional to the time, for which the heat flows. So what is T out here? T is the time in which the heat flows. And lastly, that is number 4, the quantity of heat Q is also inversely proportional. Now this is not directly, this is inversely proportional to the distance between the two phases. And that distance between two phases is also the length of the slab. So L is nothing but the distance between the two phases. Definitely this phase has temperature θ1 and this phase is the hot phase, and this phase has low temperature θ2 and this is cold phase. So Q is inversely proportional to L. So this L is also called the distance between two parallel phases. Parallel what? Phases. Or this distance is also the length of the what? Slab. Now in order to derive the expression coefficient thermal conductivity, what I do, I combine all these four quantities. I mean mathematical relation. So combining means I combine left hand side, I combine right hand side. So I write down by combining both sides. So if you combine both sides, you can see left hand side is only Q. So if you combine, it's also what? Q. Now all sign are proportional sign. Now out of 4 mathematical relation, 3 relation are directly proportional and 1 relation is inversely proportional. So if you combine, I write down proportional to A directly, bracket θ1 minus θ2 also directly, T also directly, divided by L inversely. So if you combine right hand side, So we can write this as A bracket theta 1 minus theta 2 T by L. So finally you can see Q, the amount of heat that enters and leaves from two faces or each face is given by Q is proportional to A bracket theta 1 minus theta 2 T by what? L. Now you know very well, children, that when proportional sign is removed to what? Equals to sign, you have to put some constant. So let me remove now this proportional sign to equals to sign. So after removing proportional sign to equals to sign, you can see the relation can be written as Q equals to, now I have used the symbol outer a capital K. Now this capital K is a constant, and this is a constant of proportionality, okay, into A theta 1 minus theta 2 T by what? L. And this K, which is a constant, and this constant completely depend upon the material of the what? Slab, because all the slab are not made of same material, okay. And this particular constant actually is called coefficient of thermal conductivity. So children, coefficient of thermal conductivity of the material of the slab can be expressed by the relation, and the relation you can see that is Q equals to K, A means area cross section, theta 1 minus theta 2 bracket T by what? L. Okay, now in this expression if you see, this quantity is called temperature gradient, because theta 1 minus theta 2 is change in temperature by length, and this change in temperature per unit length is also called temperature gradient. Temperature what? Gradient. So finally, the expression of coefficient of thermal conductivity simply expressed by the relation that is Q equals to K A bracket theta 1 minus theta 2 bracket close T by L. Okay. Now in the next YouTube video, we measure this coefficient thermal conductivity, okay, and we express the unit of thermal conductivity, and even we express the unit of dimension of what? Thermal conductivity. So for that we do in the next YouTube video.